Welcome. I realize that it's a beautiful day outside, and so you could all be eating lunch outside, and I really appreciate that you're here today to learn something about indoor air chemistry. So thank you for that, and thank you to the AAAS for organizing this lunch. And today you're going to hear a little bit from Dr. Marina Vance, Hugo Destales, and Rich Corsi, who will tell you about indoor air chemistry, and there will be plenty of time for questions. So I'm Barbara Turpin. I'm a professor and the chair of the Department of Environmental Sciences and Engineering at UNC Chapel Hill. I've been studying atmospheric chemistry for about 30 years. Most of that time, I've been studying how outdoor air pollution is transformed by chemistry in between the emissions from sources and human exposures. And I got involved initially in indoor chemistry, but because it turns out that most people, when they're exposed to outdoor air pollution, it happens indoors. So outdoor air pollution penetrates the indoor environment, and that's where people are exposed to it for the most part. So in the process of doing that, what I've learned about the indoor environment is that it is a major location for exposure to chemicals. In part, this is because Americans spend almost 90% of their time indoors. And indoors, people are exposed to chemicals that are brought in from the outside environment and chemicals that are emitted from people's activities, from consumer products, from building materials and furniture. They're also exposed to chemicals that are formed through indoor chemistry. For example, the oxidation of cigarette smoke, where the smoke has sorbed or stuck to all of the surfaces of the building in a smoker's home. And then that oxidation produces new chemicals, some of which are volatile, and people are exposed to those. The indoor environment is also an important location for exposures because the concentrations indoors are often higher than the concentrations outdoors. So when chemicals are emitted indoors, their indoor concentrations are often a factor of 10 higher than the concentrations outdoors. There's limited ventilation, and the emissions are very close to the people who are being exposed to them. Indoor air includes, we know about many compounds that are present in indoor air, and those include some things that are not bad for you and some things that are bad for you, and many of which we don't know if they're bad for you or not. It includes things like harmful aldehydes, pesticides, phthalates, flame retardants, bisphenol A, and PFAS compounds, all of which have some health effects. But we expect that there are a lot more chemicals in indoor air than we know about, a lot more chemicals than have been measured. And one reason I think this is true is by looking at the EPA's chemical and product database. It lists over 75,000 chemicals in 15,000 consumer products, most of which don't have any exposure data or toxicological data. We only know about a very small fraction of those chemicals, whether or not we're exposed and what their health effects might be. So having spent a lot of time studying outdoor air, one thing I've come to appreciate about the indoor environment is the influence of surfaces. So if I go home and I spray some perfume in the air or an air freshener, if those compounds stay in the air, then I'm exposed to them right away, but within a couple of hours, they've left the house, right? They've been ventilated away, and I've got some fresh outdoor air coming in. But many compounds don't stay in the air. They partition to surfaces. So that's not at all uncommon. So an example, I live in North Carolina. I try really hard to keep the cockroaches out of my house. It mostly works, right? But if I spray some pesticide in my house on a cockroach, some of that pesticide will volatilize and end up in the air. I'm exposed to that. And it will then partition between the air and all the surfaces in the house. And that includes the building materials, it includes my couch, that foam in my couch, it includes the stuffing in my kids' stuffed animals. And it'll continue to partition in and out. That partitioning to indoor surfaces really dramatically increases the amount of time that chemical is in the indoor environment, the residence time in the environment, and it also increases the opportunity there is for that chemical to react in the indoor environment and produce other things that might then volatilize and we may be exposed to. So the next three speakers will provide specific examples of approaches that we use to research and study indoor air chemistry, specific examples of the kinds of chemistry that happen indoors, and some potential solutions. And so without further ado, I'd like to introduce Dr. Marina Vance. She's an assistant professor and the McLagan Family Faculty Fellow in the Department of Mechanical Engineering at University of Colorado Boulder. In her research, she applies engineering tools to understand and to reduce exposures from everyday activities and from consumer products. She was a principal investigator of a really novel experiment called HOMEChem, and I'm sure she'll be talking about that. In her previous appointment, she was the associate director at Virginia Tech's Center of Sustainable Nanotechnology, and she has a PhD from Virginia Tech. So Nina.
Thank you, Barb, for that wonderful motivation. So, as Professor Turpin mentioned, my name is Marina Vance. I'm an assistant professor at University of Colorado. I go by Nina. And today, I'm here to talk to you about HOMEChem as an example of the types of studies we can do to probe indoor air and we need to do to better understand indoor chemistry. So, let's see. Good. So first, a little bit about my background. So I'm an environmental engineer, even though I'm in a mechanical engineering department. I've been doing air pollution-related research for about 15 years now, since my undergraduate years. So I've been exposed to many different flavors of air pollution, from doing very well-controlled laboratory studies, like using a chamber and known amounts of different pollutants, and going out into the field, going out into the real world and trying to understand what's really going on there. These are two very different facets of air pollution research, and they're both needed. So when I was an undergraduate student, and then I carried on for a few years of consulting as an engineer, I studied odors as environmental pollutants. Then I did a master's degree researching indoor air quality in hospital environments. Then my PhD was about nanotechnology in consumer products. And now, as a faculty member, I'm focused to understanding people's exposure. So how many particles of what kinds are you inhaling and touching during your everyday activities? So as you can see, the field of air quality can span a lot of different sub-areas. I've been exposed to only a few of them, and that just gives you a little bit of a flavor for it. But today I'm here to talk to you about the need for studying indoor air quality and indoor chemistry. So as construction evolves, you can tell that by our homes, right? If you are in a 1960s house versus a brand new house, you can tell that the buildings are getting more airtight. And that's for energy efficiency. That means that our energy consumption is going down, our heating costs and cooling costs are going down, and that can be pretty protective for outdoor air pollution, so you're blocking more air pollution from coming into your house. But if you look at it on the flip side, it's also exposing us further or more to the air pollution that's produced inside, and that's, as Barb mentioned, a little bit less known. When you get into the chemistry, the actual reactions and the mechanisms that happen indoors, the chemistry indoors is likely to be different from what we already know happens outdoors. And that's for these three major reasons, in my opinion, is because we have different sources, different types of air pollution being emitted. We have different types and amounts of surfaces. I mean, look at all the surfaces we have around us right now versus if you were outside. And they're different oxidants. They're the drivers of chemical transformations. Outside, the major oxidant is actually sunlight, and inside is probably going to be other chemicals. So the take-home message here is that chemistry is dynamic and complex, probably in indoor environments. So it needs to be investigated both using those, well-controlled laboratory chamber experiments and in more realistic field studies. So in the past, there have been a few collaborative, large indoor field campaigns. The one I'm going to talk to you about today is definitely not the first one. So some examples include the RIOPA study, and Professor Turpin was actually one of the leaders in that study. So they went to 100 different homes in 3 different cities in the US. They were looking for volatile organic compounds indoors and outdoors, as well as particulate matter, looking at those relationships. This project was funded by the Health Effects Institute. And then another example that I like to point out happened about 10 years later in Europe, funded by the European Union. So they went to 37 different office buildings in 8 countries, and they were looking at similar things. Indoor-outdoor relationships of particulate matter, the composition, volatile organic compounds or VOCs, etc. So one thing that these studies have in common is that they went to as many buildings as possible. So they were trying to do sort of a survey of what exists out there. But they could only focus on a few chemical species of interest because you can't measure everything everywhere. We don't have unlimited resources, right? So their focus was both on the sources indoors of air pollution and the penetration from the outdoor air pollution. Our study that I'll tell you a little bit about today was the opposite of that. So instead, we took one house and we tried to look at as many species, chemical species of interest as we possibly could measure. Our focus was still on indoor sources and penetration from outside, but we also had this more like fundamental chemistry interest on reactions and chemical and physical mechanisms that might be taking place. That we might, if we learn those mechanisms, we might be able to translate that to other situations in other homes. So that's our study. It's called HOMEChem. It stands for House Observations of Microbial and Environmental Chemistry. The study took place last summer, so a little bit over a year ago now. It was, as mentioned, a large collaborative study. We had over 30 state-of-the-art instruments, millions of dollars in instrumentation was involved, over 20 faculty members from different universities in the US and Canada. We had some industrial and governmental partners as well as over 60 researchers on site. And I'd like to acknowledge my co-PI, co-principal investigator in the study. Her name is Dr. Delphine Farmer. She's from Colorado State University in the chemistry department. And you can see the logos of all the universities involved in this study at the bottom there. So as I mentioned, we only used one house for this study, right? And the chosen house was, it's called the U-Test House. It's a test house. It's located at the University of Texas at Austin. And the house is a research instrument. It was built for research. Nobody lives in this house. This house was actually purchased over 10 years ago from a federal IGERT education and training grant. And Professor Corsi was one of the leaders, or the leader for that grant, actually. So what we have there, you can see a picture of the house on the bottom, is a 3-bedroom, 2-bathroom manufactured home. But what's really special about this house is that it's been characterized and monitored for over 10 years now. And we can control the ventilation system really well. We have all these measurements of the energy consumption. So it's a house that we already started from a point that we understand really well. And at this point, I'd like to acknowledge Professor Attila Novoselak, who is in charge of really operating, managing, taking care of the house throughout this study. So the house was his research instrument. And I'm going to go through just really quickly I'm going to use this photo from our open house day. Not everybody was there on that day, but whoever was there on that day made it to the picture. And I'm going to use this photo to just highlight some of the types of measurements we made during HOMEChem. So we did measurements of particulate matter physics, and you can see the university logos at the bottom. I won't describe everybody. So that's knowing how many particles are present at any given time, the size of these particles, and how they change, evolve, grow, or get lost to surfaces over time. We also had measurements of particulate matter or aerosol composition, so knowing what the particles are actually made of. Measurements of volatile organic compounds. So I talked about particles, now we're talking about gas phase, air pollutants. We also had measurements of surfaces in the microbiome. So some groups brought their own glass slides or painted surfaces and left them in the house for a month and then brought them back to their labs for analysis. Other groups did swabs on the walls everywhere around the house and then did either chemical or microbiological analysis back in their labs. And finally, we had some groups coming and investigating oxidants using really novel measurement techniques and other trace gas compounds to really understand the drivers for chemistry that's taking place indoors. So the experimental design for the study was pretty novel, so I always like to point it out. I mentioned in the beginning that there's this difference between very controlled laboratory studies and field studies where you go out into the world and just observe what happens. What we have here is somewhat of a hybrid because we have a house that we can't really control. We don't know what's the outdoor pollution that's coming in. We can't control that. But we controlled the activities that we performed inside this house really, really well. So in that case, it's more of a controlled experiment. We still can't control the outcomes. So we try to focus on experiments that involve everyday activities you might all do in your homes, so cooking, cleaning, and also human occupancy and their use of personal care products, because we all, in this room right now, for example, we are changing the chemistry of the air, either by the compounds that we exhale or compounds that are reacting with our skin, things like that. We, humans, also change the indoor environment, and I don't think it's something that people think about very much. So basically, this gives you an idea of what the experiment was like. We just had a very busy month, and we were performing different experiments every single day. And now we are swimming in data analysis from all of these experiments. So today, I'm just going to leave you with a few bullet points from very preliminary analysis that we've done so far. So one thing that's been proven in other studies already, and we also observed at HOMEChem, is that there were high emissions of particulate matter indoors, so PM or aerosols, especially during cooking. So the use of a stove or any kind of combustion source, but in our case, the use of a propane oven was the main source of ultrafine particles, so the very small ones that are smaller than 100 nanometers in size. The food was the main source of fine particulate matter, so what we usually call PM 2.5. And occupant movements were the main source of coarse particulate matter. So as we move around, there are particles coming off of our clothes and skin shedding and also resuspension from the floors, and that's what we were measuring there. There were many interesting chemical reactions taking place when cleaning activities were involved, and we're still digging through those data to see what that really might mean for human health and indoor chemistry. And also the role of surfaces. They evolve and they change as air pollutants interact with them and as we perform activities indoors. And the other speakers will cover that quite a bit. So my final message to you is that we have done a lot of research on outdoor atmospheric chemistry. We understand air pollution processes pretty well outdoors, but we can't really translate all of that knowledge directly indoors because the processes are as different as I mentioned already in my earlier slides. And yet, indoors is where we live. We're indoors right now. We spend most of our time indoors. So I'd like to finish by thanking and acknowledging my big team of collaborators. Some of the names are mentioned there. And I'd like to mention that we, part of our program that's funded by the Alfred P. Sloan Foundation can be seen in our website, indoorchem.org. We also have a Twitter profile. You can see it there, @indoorchem. We have a lot of blog posts and some news articles and project descriptions. So if you're interested in this topic, I'd like to welcome you to check it out over there. Thanks.